let's take a look at Electromagnetic Induction Part 2, Faraday's Law and Lenz's Law. So previously we looked at magnetic flux and magnetic flux linkage. Faraday's Law is where that magnetic flux idea really pays off. Faraday's Law states that the induced EMF in a loop equals the rate of change in the flux linkage in that loop. Okay, it's a little hard to decipher. Let's kind of try to translate that into an equation. The induced EMF is equal to negative N times the rate of change in the magnetic flux. Now, the negative sign we're going to deal with a little bit later. I'll explain why that negative sign is there another time. N is the number of loops, and then this right here is the rate of change in the magnetic flux. So if we multiply by N, then we get the rate of change in the magnetic flux linkage. So we could write this as a derivative if you wanted to, like so, but in IB physics we're going to kind of avoid the derivatives when possible, so we'll keep it with the deltas. Now, what this means, what this is telling us, is if the magnetic flux through a loop changes rapidly, then a large EMF is created, or induced, in that loop. If the magnetic flux changes slowly, then a small EMF is induced. And if the magnetic flux does not change at all, then no EMF is induced. Okay, so that's Faraday's law. Now let's look at Lenz's law. Lenz's law states that an induced EMF in a loop will generate a current which opposes the change which created the current. Let's take a look at an example of applying this. Let's say we have a situation where we have a loop, we have a magnetic field through that loop, and the magnetic field gains strength. So we go from having a weak magnetic field to a stronger magnetic field, and that's the only thing that changes. If we want to determine the direction of the current in that loop, right, because we're going to have an induced EMF in that loop, so current is going to flow, then this is how we do it. Well, let's see. In this situation, the flux upward through the loop is increasing. We're getting more and more flux upward through this loop. Lenz's law says that the induced current is going to oppose this change. So, whatever that induced current is going to create a flux downward. It's going to create a magnetic flux downward, that induced current is. And so therefore it's going to create a magnetic field downward. In order to create a magnetic field downward inside the loop, the induced current has to flow to the left on the near side and to the right on the far side. And you can use your right-hand rule to prove that. So, if the magnetic field is increasing, then we're going to have a situation where the current through the loop is going to flow like this. It's going to flow to the right on the near side. It's going to flow to the left on the near side and to the right on the far side. Now, this idea that there's opposition to change in Lenz's law, that is expressed in Faraday's law with that negative sign that we saw. So when we expressed Faraday's law with the negative sign is there because of the opposition to change in Lenz's law. Okay, let's do another example. Let's say we have a loop moving through an area of uniform magnetic field, and that loop is going to move out of that region. So within this region, within this red box, there's a region of magnetic field, and outside there is no magnetic field. So as it moves outside the region of magnetic field, what's going to be the direction of the induced current in the loop? Well, when the loop exits the region, the flux into the page decreases. There's going to be less flux into the page as it leaves that region. Lenz's law says that the induced current in that loop will oppose this. So the induced current in that loop is going to create a flux into the page and a magnetic field into the page. To do this, then the current must flow clockwise around the loop. All right. Last example. Let's say we have a loop that's rotating in a magnetic field like this. So we have a magnetic field downward towards the bottom of the page, and the loop is rotating. We want to know what direction will the induced current flow. Well, when the loop rotates from this position, the flux downward is going to decrease. The flux through this loop downward is going to decrease. There's going to be less flux towards the bottom of the page. Lenz's law says that the induced current will oppose this change. So the induced current will create a flux toward the bottom of the page and a magnetic field toward the bottom of the page that's inside the loop. In order for this to happen, the induced current on the near side of that loop has to be to the left, and the induced current on the far side of the loop has to be to the right. Last situation we're going to look at is a common problem in physics. It's called the rod on rails. And in this situation, we have a conducting rod which moves on conducting rails, forming a loop. And this is all happening in a region of magnetic field. So in a situation, I'll draw an example where we have something like this. So we have these two rails, we have a connecting wire, conducting rod that's able to move. And we'll define a couple quantities. Let's say that L is the distance between the rails, and X is the width of the loop that's enclosed here. So that shaded area is the area that's inside of our loop. If the rod is moving to the left, then the area that's inside this loop is increasing. And if the area inside the loop is increasing, then the flux into the page is increasing. And if the flux into the page is increasing, then an induced current is going to flow that'll oppose this. And that's going to create a field out of the page. So the induced current here would be counterclockwise. Okay, also, we have Faraday's law. Let's try applying Faraday's law to this situation. Well, we have that the EMF is equal to negative n times the rate of change in the flux. And the flux here is BA cosine theta. So we can get an expression for the EMF. Now, here, in this situation, the magnetic field and theta are constant. Also, theta is equal to 0 degrees, so that allows us to simplify things. The cosine of 0 degrees is always equal to 1. So this gives us that the EMF induced in that loop is equal to negative NB times the rate of change in the area. But also here, the area is equal to L times X. Now, in this example that we've created, L is constant. L is the distance between the two rails, which is never changing. So if L is constant, I can take that out front. And I get that the EMF is equal to negative NBL times the rate in change of X. But X here, that sort of width of the loop that's enclosed, that's just the speed of the rod. The rate of change in that X, that's the speed that the rod moves at. So the EMF then is equal to negative NBL times the speed of the rod. So for this rod on rail problem, if we have one loop, then we can say that the EMF is equal to, we rearrange the letters a little bit, BVL, where B is the magnetic field strength, V is the speed of the rod, and L is the distance between the rods. And if my rod on rails problem has n loops, then my EMF would equal BVL times n.